We propose tangentially elongated Gaussian belief propagation for event-based incremental optical flow estimation, TEGBP in short. Our goal is to establish an optical flow algorithm enabling efficient event-wise incremental updates. To this end, we propose an algorithm based on brief propagation, which permits incremental asynchronous updates using local message passing. We model a belief of full flow from a normal flow measurement using TEG, a Gaussian having large variance along the tangential direction of the observed normal flow. The marginal distribution TEGs with a prior equals the flow. Our C++ implementation realizes real-time processing on a CPU. The event-based camera is a bio-inspired vision sensor that detects intensity changes instead of densely observing the intensity. Thanks to the novel sensing mechanism, it has several advantages over conventional frame-based sensors. We consider an event-based camera is the best sensing device to realize optical flow estimation at the extreme low latency. An existing method using local plane fitting of events could utilize the sparsity to realize efficient incremental updates realizing low latency estimation. However, its output is not a full optical flow we want to estimate but the normal component of the full flow. An alternative approach using a frame-based deep neural network could estimate the full flow. However, its intensive non-incremental dense operation prohibits the low latency estimation. Our research goal is to establish a sparse incremental algorithm that could estimate full flow. Normal flow tells the line on which the flow exists, and we cannot tell the full flow uniquely. We model the probability of full flow using TEG, a Gaussian having large variance along the tangential direction of the observed normal flow. TEG could also incorporate the fact that the full flow is more likely to exist around the normal flow. We need some prior knowledge, such as the true flow being smooth spatially, to estimate the full flow. Here, psi is the probability distribution of TEG, phi is the prior distribution between neighbor nodes. We solve the marginalization of the factor graph by belief propagation to estimate the full flow. Given a valid prior, the marginal distribution of TEGs and the prior equals the full flow we want to estimate. We can compute the marginalization using local message passing, which could be executed asynchronously for each incoming event. When implemented on CPUs, each thread computes a sequence of passing triggered by each incoming event. They are parallelized, and the full flow is updated asynchronously. The estimated full flow could be retrieved at any time. This plot reports the runtime by changing the number of cores. Thanks to the asynchronous nature, runtime monotonically decreases with respect to the number of cores. We realized the real-time estimation at the quasi-event rate in real-world datasets. This is a result on MVSEC. Looking at the circled region, our TEGBP estimates a reasonable flow. This is a result on DSEC. We present TEGBP, a novel belief propagation-based formulation of full flow estimation enabling incremental flow estimation. Please visit our poster session and check out our code.